Evening and welcome back. We've been desperately trying to improve the screen during the interval. If it dies entirely, there is another lecture free over the other side of the college, but we're going to keep our fingers crossed and hope we survive the next two lectures. So it's my great pleasure to introduce Dr. Louise Alexander. Louise did her BSc and her recently completed PhD at Birkbeck as a maturity student in Earth and Planetary Sciences, and loves Birkbeck so much she stayed on to be a postdoc here. She is the co-chair of the UK Planetary Forum for the last 3 years, and Louise is going to talk about analysing the Moon. What can we learn from the Apollo samples? Louise Alexander.
Right, okay, so hopefully everything will work okay, but we'll sort of muddle on through. So I'm working for Professor Ian Crawford, and we've spent a lot of time looking at lunar samples. I was doing that for my PhD, and I've carried on to do that for my postdoc. So what I'm going to be talking about is what we can actually learn from the Apollo samples that were brought back to the Moon between 1969 and 1972. But in order to do that, I'm just going to run through the different types of lunar samples, why they're important, what we can learn, and then I'm going to come on a little bit to the sort of research that we've been doing as well. So lunar samples, the Moon is currently the best sampled non-terrestrial planetary body. And the lunar samples fall into two main categories. So we've got those returned by human activity, so those are the Apollo missions that I just mentioned between 69 and 72, and those returned 382 kilograms of material. But in addition, there were the robotic unmanned lunar missions, which brought back just 326 grams, but a really sort of valuable addition. But as well as that, we've also got the lunar meteorites, so there are more than 240 samples making up 118 individual meteoroids. And they're really important because they've added a lot to our knowledge. They've given us a lot more diversity than just those from the Apollo sites, and they're mainly collected in the Antarctic. So I put a couple of images up here. This is Dr. Catherine Joy at the University of Manchester, and she's actually been on the ANSMET team a couple of times, going out into the Antarctic searching for meteorites. And there are also a lot from northwest Africa as well that are found there. And as I say, they've sort of really added a lot to what we already know. But there are two main problems with looking at meteorites. One of those is that they're very altered sort of a lot of the time. So they can suffer from shock and weathering as well. So that's a problem. And of course the other problem is that we don't know whereabouts on the Moon they've come from. So we know they're from the Moon because we can tell that through their chemistry and through their isotopes, but we don't know whereabouts. We can say, well, you know, it's probably from this sort of area, but we can't pinpoint a location. So again, sort of human sampling of the Moon, these are the sort of Apollo and lunar sites that are highlighted, and what you'll notice is that it's kind of a really restricted region of the Moon. It's sort of confined to the near side, broadly equatorial as well. And that's partly because it's a good return to Earth trajectory. It's been intensely studied by telescopes from the surface of the Earth. And also, these darker Mare basalt regions have less craters, so there's a safety aspect to that as well. And so you can see from looking at this why it is important that we've got meteorites from other locations, even though we don't know exactly where they're from. And so the rocks that we get from the Moon, they're classified in a lot of different ways. So they're classified according to their texture and to their chemical composition and their mineralogical composition. But if we look at the Moon from the Earth, we can sort of break it down into some really broad categories. So you can see that we've got the highlands, the lunar highland rocks. These are the pale regions on the surface of the Moon. And these are the sort of really ancient crusts that we'll look at in a bit more detail. But in addition to that, we've got the darker regions, and these are the Mare basalts. These are sort of volcanic lavas. And even from the Earth's surface, we can sometimes see some slight differences in colour in these darker regions. And that kind of gives you an idea that there are some subtle variations in their chemical composition. And then in addition to that, we have some non-mare volcanics in isolated areas and some pyroclastic rocks, and we'll come on to those shortly. So the lunar highland rocks, as I've said, these are derived from the original anorthositic lunar crust. So anorthosite comes from the mineral anorthite, which is a form of plagioclase feldspar, and these are the oldest rocks on the moon. But because they're so old and there's a lot of impacts on the moon, they've been kind of fairly pulverised, so there aren't many pristine examples that are available, and most of them are brecciated and contain clasts of other bits of rock as well. And then we've got the mare basalts. A lot of my work has been looking at mare basalt samples. They're the dominant type of volcanic lunar rock, and they tend to infill sort of the impact basins, and they're very fluid flows, very iron-rich fluid flows. But there's a lot of variety in terms of the chemistries and the textures. So we can see here we've got a vesiculated sample, so there's obviously been some exsolution of gases once that's come onto the surface. And then in addition, we've got these other non-mare volcanics and the pyroclastic rocks. So if you think about places like Hawaii, where you've got fire fountaining, for example, this is the sort of thing that has formed these. And the most famous example is probably the orange soil found at Shorty Crater on the Apollo 17 mission. And the colours formed by, they're quite rich in titanium, which gives it this sort of orangey colour. And then the surface of the moon is covered in this pulverised layer of rock. And this is called the lunar regolith. So Hilary touched on this, on the surface regoliths of other planetesimals. And most of the samples that we've got are regolith samples, so they're sort of all these tiny fragments of rock, but the composition generally reflects the underlying bedrock, although you can have material that's been brought in from elsewhere. So rocks are composed of minerals, and I don't want to sort of get into this in too much detail tonight, but these are the basic silica minerals and ilmenite, which is an iron titanium oxide. And so basically we concentrate on these minerals. There are others, but they're actually sort of mostly very rare, and we certainly don't have all the sedimentary rocks that we have on Earth or some of the ones that we have on Mars, so there are no sort of things like clays to worry about on the moon. So it makes it a really nice, simple place to study. Sometimes. I mean, there are complications. So what have these samples actually taught us? Well, they've taught us so many things, and I can't really sort of fit it all in, but I'm going to just run through a few examples. So again, as Hilary touched on, one of the preferred theory for the formation of the moon is the giant impact theory, where you have an impactor that's collided with the Earth, and material has spun off, cooled, coalesced, and formed the moon. It's not the only theory, but it's kind of currently the favourite. Different models will have different sizes of impactors, and there's still ongoing work with that. But one of the reasons that the Apollo samples have helped with that is because they've provided samples that show evidence that there was a planetary melt on the surface, and also that they're very, very similar to the Earth. So lunar samples are very similar to terrestrial samples in terms of their isotopic composition. So they must have formed very, very close together, or they were part of the same body. The geological evolution of the moon is something else that we can tell by looking at lunar samples, because the majority of the samples that we've dated so far are between 3.9 and 3.1 billion years old. But there's a much older sample. There is a younger one as well, which I meant to put on here but didn't. But when you look at the remote sensing data, it actually covers a much wider range of ages. So the duration of lunar volcanism is something that's quite important to sort out, because it sort of relates to the cooling history as well. So that's something that's ongoing. The more samples that we date, the fuller picture that we have, to try and sort of tie up the sample science with the remote sensing. Lunar samples, so the Apollo samples have also helped tell us about the geological evolution of the Moon. So because we've got this anorthosite, like this frothy, crustal, light, low-density layer, the idea is that in order to form that, you have a magma ocean. And the idea at its most basic is the lighter minerals float and the denser minerals sink, which kind of makes sense. And you're left with this material called creep, which is potassium, rare earth elements and phosphorus rich, which is why it's called creep, that doesn't readily go into any of the minerals. And then following that you have volcanism and impacts. So all this has all come from sort of studying the samples that relate to these different effects. And it's much more complex than that, actually. This is a really, really simplified model. And the more that we study the samples, the more we learn about this. Now, most of the dating of planetary surfaces, aside from the Earth, is done via remote sensing, and it's done via crater counting, and it can get quite complex. But again, the most basic idea is if you have one area with a lot of craters and one area with not many craters, then the one with a lot of craters is going to be older. It's been exposed longer, and it's had all this cratering. But you need to calibrate that by having the actual samples from some of these areas to date, so that you can date them. You can then use this information not only for the Moon, but you can also alter different models and use them for Mars and the rest of the solar system as well. So it's really, really important work. So now what I'm going to do is I'm going to sort of drill down, show you what we can do with just a tiny little bit of material and how that can add to this big picture. So as I said before, a lot of the work that I've done has been on the Apollo 12 samples, and this is the Apollo 12 site. And there were two EVAs, extravehicular activities, and they returned 34 kilograms of samples. So what we're going to do is we're going to just look at one sample that's come from this crater here at the furthest end, and it's actually, it was taken from the bottom of a 20 centimetre trench. And another lovely thing, these are all the Lunar Reconnaissance Orbiter images, is that you can put them together and you can get, so that's a whole lunar day on the Apollo 12 site, which is just an amazing thing to see, because you see different things at different illuminations. So this is, if anyone hasn't seen any of the Lunar Reconnaissance Orbiter images, then I suggest you all go and look at those and at the different landing sites, because there's really some lovely stuff up there. And so we can go, this is again why it's so different to looking at meteorites, because this is the actual sample location. It's an image that was taken by the astronauts. This is the trench. The sample that we're going to look at came from the bottom of that trench. So we've got an exact location and a field site. Okay, so so we're going to look at a chip from this sample. This is what we get. And they're tiny, tiny little grains. So at first, the first thing you might think is, you're not going to get a lot of information from this. What can you possibly get from this sort of like, this is a magnified image of that grain? Very, very little detail. So between 2 and 4 millimetres when we get them, and we cut them in half, and we make the most of every last bit of this material. But you put it under an electron microprobe, as Hilary mentioned earlier. You fire a beam of electrons at it, and you can get this backscattered electron image, which suddenly, it's really opening up this sample. It's suddenly getting a lot of detail about the textures. You can see zoning in the crystals, which tells you that the melt has changed over time. You get a cooling history, so you can see that these crystals will have grown slowly, and then these other ones will have grown rapidly at the end of the stage. All this sort of information that you're getting once you put it under the microprobe. So electron microprobe analysis is the bulk of the work, certainly that I did for my PhD. So you can build up these backscattered electron maps. We can also look at mapping individual elements. Another thing that we can do is that we can take different areas and get a chemical analysis, get a bulk composition for that. And then we can use wavelength dispersive spectrometry and actually look at the individual minerals as well. So you get a really full picture just from this one little sample. And then we can also do mass spectrometry. So we have laser ablation, ICP-MS, and you can see on this on this image here, you can see all the little circles. That's where we've zapped it with a laser, and then we analyse the material, and that can give us the trace elements. So it can, you know, sort of give us a lot of detailed information. And then we can actually use the whole sample and do a bulk release noble gas mass spectrometry. We can do that to date the sample using argon-argon dating. And also what I'm going to come on to in a bit is that we can also analyse the noble gases and different isotopes. So, you know, there's nothing that we don't do to this tiny bit of material. So just to show you, this is an element map of the image. So this is the grain, and we've assigned each element a different colour, and then you can sort of build up a map that sort of to compare to your backscattered electron image. It's giving you all the time, it's giving you more detail about the composition and the textures and what this, you know, what this rock's made of. So the pyroxene stands out as quite green here because it's got a lot of magnesium in it, but there's also some more iron-rich pyroxene as well, which is redder, and the blue is silica. So you just start to sort of build up the chemistry this way. And then what can we do? Well, we can compare it with all the other samples in the batch. We can see the differences in the chemistry, we can see the differences in the texture. So we're getting more and more information all the time. And then I have no time to go through this, and I'm sure you're quite relieved. I'm certainly relieved. It's just to show you, this is just from the pyroxene crystals in the samples that we've looked at. So just from one mineral phase, you get all this information. We already know that there are a variety of basalts at the Apollo 12 site, so we can look at the literature, we can compare it with all the other data on all these different types of basalts, several different lithological groups. And then finally, this is what we're aiming for, is to come up with a cross-section to give us an idea how these samples relate to each other, relate to the other flows. And one of the things that we found is, for example, that there are so few feldspathic basalt fragments. These are basalts that are rich in the mineral feldspar, that they must be at a very deep level. They're also slightly older than the others. So, and that means that very few craters have been able to excavate that layer. So ultimately, this is what you're doing with these tiny bits of material, is you're building up a bigger picture of the site. Okay, so that's shown you what we can do with a really small sample set. And now we're like, oh, you know, we've still got some material left, and you know, you don't want to waste this stuff, right? Because it's so valuable, and if it goes back, it might not be used again. So I'm just going to tell you quickly about our new projects that we're just starting. So this is the Milky Way galaxy, and the sun is over here. And the solar system travels around the Milky Way galaxy. In fact, it's been around the centre about 20 times since it's existed. And during that time, sometimes it's going to pass through some dense areas and some of the spiral arms, and you're going to get a lot more radiation because you're going to have star-forming regions. You might have supernova remnants, and so the Moon can potentially record material from these events in a way that the Earth can't as effectively because of the atmosphere and its magnetic field and plate tectonics. So, you know, it's much more complex on the Earth, whereas the Moon has this sort of really ancient surface and no atmosphere. So everything that's happening is going to kind of affect the surface of the Moon. So the idea is that we can potentially unravel some of this history. It's kind of that's a big ask, right? But we're going to start looking at that and see what we can actually do with that. And so in order to do that, what we're going to look at are cosmogenic isotopes, because so galactic cosmic rays are these high energy particles originating outside the solar system, and they're accelerated by supernovae. And when they interact with atoms in geological materials, they produce these different isotopes. So there's a variety of those. The only ones that we can measure actually at the moment for our project are helium-3, neon-21 and argon-38. But nevertheless, that's great, isn't it? We've got this instrument over in Geocron at UCL, noblesse mass spectrometer, and if we can measure the concentrations of these isotopes, then potentially we can see how they have varied over time and start to build up a bit of a history of the solar system and the Milky Way. And it's not as simple as that, because the existing surfaces, so the Apollo samples that we have, and I'm not knocking it, it's really, really great to have them, but they're from the surface regolith, and they have unknown shielding history, so their history is really, really complex to unravel. There's a lot of corrections, a lot of uncertainties, and it's very, very difficult to sort of really build up any decent sort of picture. So what we're doing is we're just seeing how effectively we can measure the concentrations, which is a good start. And ultimately, what you really want are these paleoregoliths. So the idea is that you have a lava flow on the surface of the moon, and then because you've got the introduction of other material, you've got sort of the pulverisation and the impacts, and you build up this regolith layer, and then you get another lava flow, and that traps the regolith layer, and then that builds up its own regolith, and then that gets trapped as well. So really what you want to do is drill through some of this material and get at these different horizons, so you know they come from kind of different time zones. And these areas do exist. So again, Lunar Reconnaissance Orbiter images, you can just find anything. These are some crater walls with layers. So you can see that if you could just get through some of these and have this sort of giant core of material and analyse it, you could really get some useful information about this. And it's actually quite important, because if you look at the history of the galaxy and our journey through it, is also important to, for example, things like when life developed and how it might have affected life in the past. So that's kind of as far as we got. It's very difficult, and but the samples that we have certainly contain a wealth of information, not only about the moon, but also the Earth, about the solar system, and potentially about the galaxy as well. So, and the knowledge is increasing. We've got all this really, really great equipment, and we can really analyse this stuff really well. But in order to really answer some of the big questions, we need appropriate samples. So, like I was saying about the regoliths, and this really is going to require some advanced drilling into the subsurface in order to get this. So, take-home message: we need to go back to the moon. Okay, that's it. Thanks.
Questions, Louise?
In terms of the paleoregoliths, what was the time period that the moon was volcanically active?
Well, yeah, so, I mean, the estimates vary, certainly between 3.1 and 3.9 billion years there were these lava flows, and there are slight variations between the ages, and you can see the layers in those craters. So yeah, I mean, hopefully you've got enough of a time variation between them for a decent regolith to have built up, but it's an uncertainty. I agree with you. Yeah.
But then the most recent you're going to get is 3.1, you're saying?
It is. I mean, you've got the surface regolith now, but it's really hard to unravel. But if you're looking at that in comparison with some of these older ones, then that would put a different context on it, I think, and make it easier. So,
in terms of this new project of mapping the solar system's journey through the Milky Way, do we already have a sort of a map of zones in the Milky Way through which the solar system must have passed, or would we be building up that map from what we find on the moon?
Right, both actually. Yes, we do, and yes, it's been modelled, our passage through that. But this would certainly, ultimately, and I have to say, you know, at the moment we're just checking we can analyse this stuff really well, and we can separate one from another, and we can unravel the history. So this is in advance of a much bigger project, which will do that. But ultimately, you're absolutely right. We would look to improve the accuracy of those maps that do exist, and certainly the models that do exist. Yeah.
Any more questions? If not, I'd like to thank Louise again. And our final speaker this evening is Natasha Almeida, who graduated from UCL with an MS/MSci in Planetary Science and is now the Assistant Curator of Meteorites at the Natural History Museum while doing her PhD at Birkbeck. And she's going to explain how you look inside meteorites and other